Calc students, Dr. Schrage here, and just like all your teachers at early college, we really miss you guys, and we're proud of all the progress you're making. And don't fall behind, because things are gonna, be getting back up to pace here. And I know some of these deadlines get set kind of far out, but that's an EVSC thing, not us. Make sure you keep up with your work, okay? All right, today we're moving forward to the next section. I think it's 4.4 in your book, although I have to admit I didn't write that down. Remember, I always make you a handout. This one's called Mean Value Theorem Handout. And I think that this is going to be helpful to you as we go through here. Again, it's up to you as to whether you print it or you just got it up on a screen next to you as we're doing this. But I want to go through this here. Your book talks about mean value theorem as like one of the most important things that you're going to learn in a calculus class. And, well, kind of yes and kind of no. Actually, mean value theorem is buried in the proofs of tons of things in a calculus course sequence, especially in Calc 2 and Calc 3. But that doesn't mean we're doing that right now, and I'm not sure that I would agree that this is the most important thing. That being said, it is in the goals for Ivy Tech. It's part of how you get dual credit and so on. And so we're going to do it. It's just I'm not sure it's the most important thing. Now, before we get to mean value theorem, we actually start with a special case of the mean value theorem called Raleigh's theorem. I think it's pronounced Raleigh anyway. The reason why I'm not entirely sure is because I remember when I was in college, Father Ports, who was the Calc 1 teacher, I think I've mentioned him before, old Jesuit priest, he called this the jump rope theorem. And that's actually kind of a helpful way to think about what's going on here. Raleigh's theorem is for special situations where we're talking about the value of some function over some interval from like A to B along the x-axis. So like here, from A to B along the x-axis, or from here from A to B along the x-axis. And what's special about the functions that Raleigh's theorem can deal with, or the jump rope theorem can deal with, is we want the endpoints to be the same height above the x-axis. A fancy way of saying that would be that whatever your function is, f of A has to be equal to f of B. So your starting points value and your ending points value have to be the same. And the reason why they call it a jump rope theorem is because it kind of looks like a jump rope. I mean, if you were jumping rope, if you had the two ends of the rope at different heights and you're trying to jump it, that would be some pretty fancy jump roping, right? When you're jumping rope, the two ends of the rope are at the same height. So like here we could, I don't know, somebody's jumping over the rope here. I don't know, I didn't really think this through very well. And here's somebody's jumping the rope over here. And, well, this would be some pretty fancy jump roping, okay, with a rope doing this. But you can see how the height of the beginning and the ending point of this function's interval is the same height above the x-axis. And Raleigh's theorem is actually a pretty common sense thing. It actually is an enormously difficult proof to show that it's true. But it shows that as long as this is true, where the ending point and the beginning point and the ending point both are the same distance above the x-axis, in other words, f of A is equal to f of B, then there has to be some value c between A and B, maybe lots of values c, but there has to be at least one, where the derivative of the function at that place is 0. That might sound like kind of a hard thing to think through, but when you realize what that means is there has to be a place between A and B where the function is flat, where its derivative is 0. Well, actually, once you start drawing yourself some little sketches of this, it's clear it has to be true. To get from here to here, there's going to have to be a place where you turn around. To get from here to here, there's going to have to be a place where you turn around and the function is flat. Same with here and here. And so, actually, once you like sketch a couple of these guys or whatever, Raleigh's theorem is almost more of like a common sense kind of thing. Although, like I said, it's a theorem. It's been proven, and it's actually proven in the book and so on like that. But actually, we aren't going to worry about the proof, as I mentioned on page 2 of the handout. It's just, we got enough to deal with this semester, okay? But there's all kinds of things, Raleigh's theorem is mostly useful because it gets us toward the mean value theorem, which is the main purpose of today's activity. But let's actually do an example from your book about Raleigh's theorem. It says we're going to have this function, f of x, this is on page 2 of your handout, f of x equals, and I guess I'm using x squared plus 2x, and we're going to have some interval from -2 to 0 along the x-axis here. And what it says in the problem here, in the example, it says verify that this function satisfies the criteria of Raleigh's theorem, and then find the value c over that interval where the derivative of f at c is equal to 0. Okay. All right. So what we need to do, this is going to make some kind of graph, and what we need to say, here is our value A, and here is our value B. This is the starting point and the ending point of that interval. And for Raleigh's theorem to be okay, for the jump rope theorem to be okay, what we need to do first is show that f of A is equal to f of B. Alright, so what we would do is we would plug in -2. So -2 squared plus 2 times -2. And we're asking ourselves, is that equal to the endpoint when we plug in 0? Which would be 0 squared plus 2 times 0. Well, hopefully it's clear that this side is equal to 0. And over here, -2 squared is 4, plus 2 times -2 is -4, and 4 plus -4 is 0. So it checks out. Raleigh's theorem will work on here. Now there's a couple other, what's a good word? There's a couple of other caveats on Raleigh's theorem, like the function has to be continuous, it has to be differentiable, but there's no problem. This is just a polynomial. We're not going to have any problems with, like, maybe there's no such thing as a derivative, and so, no, we're going to be fine with that. Alright, so according to Raleigh, this should work. We should be able to find Raleigh's theorem checks out for this function. Therefore, according to Raleigh's theorem, there is some value c that's between the beginning point and ending point of our interval, where the derivative of the function at that c is equal to 0. In other words, the function is flat at that point. So let's see if we can actually figure out what that would be. I'm going to clean some of this stuff off of here. And, alright, so if that's our original function, what we're looking for is the place where the derivative of this is equal to 0. So Raleigh's theorem guarantees that there's going to be such a place, so let's find the derivative. The derivative of this is just 2x plus 2. Alright, and Raleigh's theorem, I'll just write RT, we know that this can be set to 0, and there's going to be some value of x that makes this work. Pull that and 2 over to that side, and x is equal to -1. This is that value of c, and remember c needed to be between the starting point and the ending point of this function, of this interval, and it would be a place where the derivative is equal to 0. Let's actually prove that to ourselves. If we plug in -1 in here for x, we'd have 2 times -1, which is -2, plus 2 is 0. The derivative here is equal to 0. So we have found the value of x equals c, in this case c is equal to -1, where the function is flat. Now at the bottom of page 2, I actually drew you a graph of what this looks like in Desmos. Let's just sketch it up here real quick. In this particular case, our original function, this guy right here, looks something like this. All right, where like this end is at the point -2, 0, and this is at the point 0, 2. I'm sorry, 0, 0. Notice that this satisfies Raleigh's theorem because the beginning point and the ending point are the same height above the x-axis. In this case, the height is 0. So Raleigh's theorem guaranteed to us that there had to be some place between -2 and 0 where the function's derivative was 0. That is to say, the function was flat. And we found that place. It's at c equals -1. So at x equals -1, y equals whatever that would be, -1 squared is 1 plus 2. Looks like that's probably at -1 comma -1. Although I didn't, yeah, that's right. We have that point that we're looking for, the place where the function is flat. Alright, so we're good. Raleigh's theorem makes good sense. It's usually not too hard to convince students that Raleigh's theorem has to be right. I mean, it just kind of makes common sense. You can't really picture any way to make, if you've got two dots at the same height above the y-axis and you need to connect them with some kind of curvy line, no matter how you connect them, there's going to be at least one, maybe multiple places where the derivative is going to be 0. You've never thought about that probably or anything like that, but the idea behind it is not tricky. But then we take that forward to the mean value theorem. It turns out that Raleigh's theorem is actually just a special case of the mean value theorem. Mean value theorem is a more general idea than the Raleigh's theorem. We're going to let go of this idea. Remember, Raleigh's theorem required that we had to have that the starting point and the ending point were at the same height above the x-axis. That's why it looked like a jump rope, right? But Raleigh's theorem, I'm sorry, the mean value theorem lets go of that and says we don't need to worry about that. It can be not equal to each other. Then what will that mean for the mean value theorem? Well, I really liked one of the figures that was in your textbook, so I cut and pasted there on page 3 of your handout, and I'm going to try to sketch this guy here a little bit for you. Where we have some kind of graph of some function that looks something like this. All right, where we have some interval that goes from A to B along the x-axis, and this is f of A. This point here would be A comma f of A. And this point right here would be B comma f of B. They're not at the same height above the x-axis anymore. Mean value theorem lets us get rid of that particular thing. No longer really looks like a jump rope or anything like that. And on this diagram here, if we wanted to, we could connect the starting point and the ending point with a straight line here. And that straight line has a slope. It connects this point here at B comma f of B to A comma f of A. And this is called the secant line. We've used that word secant before. Like it kind of connects two, it's the straight line that connects two spots on the function. And what we care about here is the slope of the secant line. That slope of that secant line, well, wait. You've been doing that since like Algebra 1, maybe even like 8th grade math or something like that. Rise over run. It's going to be the difference between the ending points. I'm sorry, the difference between the y heights, like f of b and f of a, and the difference between the x coordinates of it. This is your slope of the secant line. We'll sometimes use the symbol m secant here for the slope of the secant line right here. That is the line, the straight line that just connects the starting point and ending point of our function right here. All right. What the mean value theorem is telling us is very related to what Raleigh's theorem was telling us. It's going to tell us that there is some place C between A and B, at least one such place, where the slope of the function there, in other words, f prime at C, is equal to that slope of the secant line. In other words, there'll be some place, maybe multiple ones along the way, where the tangent line there, I can't really draw it very well, there, in this case there's two such places, is the same as the slope of the secant line. See, I can tell because they're parallel. So there's a place right here, there's a perfectly good C right there, and there's a perfectly good point C here. In this case, there were two places along the way where the slope of this tangent line, the derivative of the function at that place, was equal to this way of writing the slope of the secant line. That might not seem very important, and that might seem like much less intuitive than Raleigh's theorem was, but you can kind of start sketching yourself some examples of this. I don't know, make yourself another weird function here. Here's our secant line, and there's got to be at least one place, again in this case there was two, where the tangent line to the function there is parallel to that secant line. This is going to turn out to be like way important in like all kinds of proofs later in this class and in Calc 2 and Calc 3 and so on. Is it exactly the most earth-shattering thing in our course and for our purposes? Not exactly. I mean, I do like the way it's written in the bottom of page 3. I actually cut and paste that right out of the textbook. But, you know, it's a weird and wonderful function rule, and it's going to end up meaning all kinds of important things. But if you are wondering why the heck it's called the mean value theorem, that is a legitimate question. But we'll get to that in just a little bit. Instead, first I want to do another example from the book to show what we can do with this. This comes from the book. I have to admit I did not write down on page 4 which example this is. But you can flip through on the book real quick and see if you can figure it out. Excuse me for a second. Okay. So here's the example I'm doing on page 4. It says, for the function given below, on the interval from 0 to 9, so that's the span or interval of values on the x-axis, it says find the value c between a and b so that the derivative of the function at c is equal to the slope of the secant line. And the function that we're working with is just f of x is the square root of x, which I'll write also as x to the 1/2 power, because that's going to be helpful the way we're going to do it. All right, so first we need to figure out, our first step is going to be find the slope of the secant line. The slope of the secant line. All right, so the slope of the secant line, remember, was f of b minus f of a all over b minus a. And remember, this number here is a, that's the starting point, and that number is b, the ending point of our function. All right, f of b, square root of x is f. b, f of b will be the square root of 9, which is 3, minus f of a is 0. Square root of 0 is just 0. b minus a, b minus a. It's going to be 3 over 9, or 1/3. So here is our slope of the secant line. We'll make a graph of this just a little bit, or you can peek ahead to the top of page 5 in your handout. But this is the slope of the secant line. When we draw this function, that's what the straight line that connects the ending point and the beginning point of the function has a slope of 1/3. Now, the mean value theorem is guaranteeing that there's at least one place in that span from a to b, or from 0 to 9, there's at least one place, c, where the derivative of the function at that place is equal to this slope of the secant line. Maybe more. In this case, it turns out to just be 1. So, all right, if we're going to do that, apparently we need to know the derivative. All right, so here's our original function, and now we're going to find f prime of x. All right. Well, f prime of let's see here, I'm not being very neat. So f prime of x is equal to 1/2 x to the negative 1/2 power, which is 1 over 2 times the square root of x, if that helps you. All right, so that's our derivative. And what we're saying here from the mean value theorem is there is some value c between 0 and 9 where that derivative equals 1/3. Okay, so let's actually put that in there. Oops, let me straighten this out a little bit here. So 1 over, here's our derivative, is equal to 1/3. We know from the mean value theorem, that this has to be true. There has to be a place where this happens. Oh, I can hear my phone ringing. Okay. This is messy with all this stuff in the denominator, not in the numerator, so I'm going to take the reciprocal of both sides and switch it to 2 times the square root of x equals 3, which means the square root of x is equal to 3/2, which means x is equal to 9/4. That is the value c, and you can see it's between 0 and 9. This is, what, 2 1/4? So it is between those two values, and it is where the derivative of this function should be equal to 1/3. But that is hard to see, just like glaring at this screen right here. It is not obvious what this all means. Now, I tried to make a graph of that on the top of page 5, and I don't know if I made things better or worse. So let me try to sketch this thing again for you up here. Again, this one, though, is an example in your book. I apologize I didn't write the number, the page number or anything down. But you can flip through this section of the text and find the same guy. But let's draw this here. Remember, our function was just square root of x. That function looks something like this. And we're going from the starting point of the function, which is at 0, 0, and going out to the ending point, which was at 9, 3. This is the interval. The interval that we cared about was along the x-axis from 0 to 9. 0 was our a, and 9 was our b. And if I can do it neatly here, we could connect the starting and end point here. I didn't do it very well, but we'll call that good enough. That is our secant line. It just connects two places along the function along the way, and it had some slope, m secant. And if you remember, that was equal to 1/3. The slope of that line was 1/3. Okay, but by the mean value theorem, we knew that there had to be at least one place between a and b where the derivative was equal to that. In other words, where the slope of the tangent line was the same as the slope of the secant line. And in fact, we found it. It was at 9/4. Was that right? 9/4? Yes. So at 9/4. So someplace like over here, roughly, there was a place where the tangent line is parallel to that secant line. They have the same slope. That's what we're looking for here. We're trying to find the place along the way. Other places along the way have tangent lines too. They're just not the same slope. They're not parallel to that secant line. Only one place in this case, but the mean value theorem guarantees that there has to be at least one place along the way where that works. Whew. Okay. Why is this called the mean value theorem? Let's do an example that's going to shed some light on that. This is going to involve like a story problem with velocities and stuff like that. And I know some of you aren't nuts about that. Let's be careful about it. So on page 5 we start out an example. This happens, I did label this one. This is example 416 from your book. And it says, if a rock was dropped from a height of 100 feet, its position t seconds after it is dropped until it hits the ground is given by the following function. So its position as a function of time is equal to negative 16 t squared plus 100. This is what describes the height or position of the rock at time t. So like for example at time t equals 0 at the beginning, this term goes to 0, the height of the rock is 100. But like 1 second later, t equals 1, t squared, what is that going to be? 84 feet above the ground. And at 2 seconds, and you can do the math or whatever here, and it's like 20 feet above the ground or something like that. This is the position of the rock. Now, the problem has 3 steps. It says determine how long it takes before the rock hits the ground. B, find the average velocity of the rock in the interval between when it was released and when the rock hit the ground. And C, find that time t that is guaranteed by the mean value theorem to be when the instantaneous value of the velocity of the rock is the same as the average velocity of the rock over the period of time. Alright, the first part is not such a big deal. We want to find out when the rock hits the ground. Here, I'm going to draw myself a little separator here. So we're going to do part A first. When does the rock hit the ground? Well, the rock hits the ground when its position is 0. It's no longer like 100 feet above the ground or 84 feet above the ground. Its height is 0. So 0 equals negative 16 t squared plus 100. And we're just solving for the t that makes this true. I'll pull that 16 t squared over to the other side. I'll pull that 16 back. And that makes t equal to 10/4, or 2.25. Is that right? No, it's 2.5. 2.5. Okay. In other words, it takes 2.5 seconds for the rock to fall to 100 feet. At time 0, it was 100 feet above the ground. At time 2.5, it is 0 feet above the ground. Alright. So we got part A done. Alright, now, part B asks you to find the average velocity of the rock during that time. Alright, we know at time 0, the height was 100 feet. We know at time 2.5, the height of the rock was 0 feet. Alright, so, again, it's just a change in height over change in time. We went 100 feet in 2.5 seconds, that's 40 feet per second. Now, okay, in other words, in 2.5 seconds we went 100 feet, so apparently it is 40 feet per second. Now, I'm going to go ahead, I'm not sure, do I mean plus or do I mean minus here? Well, I want to be careful about this here. Let's think it through the way the book did here. We'll call this time, this is A, the starting point, and this is B, the ending point. So let's see, f of B is 0. Remember, let's write the function back down again here. That's slope of the secant line, which is our average velocity, is f of B minus f of A all over B minus A. Now we're not using F, we're using S here because it's the position, but it'll work the same sort of way. So 0 minus 100 over 2.5 minus 0 is negative 40 feet per second. So the velocity here is actually negative because we are going down the y-axis here. We're actually getting closer to the axis. So our velocity here is actually negative. Okay. Now we have that pieces of information. Let me clear some of this out. We can use the part that actually involves the mean value theorem and so on. All right. All right. In part C, it asks you to find the exact moment when the instantaneous velocity of the rock is equal to the average velocity over its whole trip. I guess we're going to need to know the velocity of the rock at any given time. I know students get a little bent out of shape about story problems and the relationships between position and velocity and so on. But remember, the velocity is just the derivative of the position. So it's going to be negative 32t plus 0. And in other words, at any given time t, we now can find the velocity. And the mean value theorem is guaranteeing that there is some time c where this is equal to an average velocity. In other words, the mean value theorem is telling us that there is some time here where this is equal to the average velocity. Alright, we can pull that negative 32 over the other side, and you get 40 over 32, which is 5/4. In other words, at time t equals 5/4, the instantaneous velocity, the speed the rock is going at that exact time, is exactly negative 40, which was the original speed of the rock. I'm sorry, was the average speed of the rock. Alright, now, I think a diagram is going to help that quite a bit. No. Sorry, Xavier apparently wanted to help or something like that.
No, I had a question.
Okay, well, I will help you that. I've got about 5 more minutes here. Okay? Alright. Alright. So, a diagram is going to really help this. And there's a diagram on page 7 here. I made it in Desmos there. And what we're doing here is we're making a graph where we got time on the x-axis and we've got the position on the y-axis here. And the rock starts up here at a height of 100 and falls to the ground. Alright, so with time, at first the rock is barely moving and then it goes really fast down to the bottom here. We could even label these points here. This is at time 0, the height is 100. And this is at time 2.5, height is 0. This is the height of the rock here. Alright, now, we could just look at the starting and ending points and say, in 2.5 seconds, we traveled 100 feet. So we had already done that before, where we had shown that that means that the average speed was negative 40 feet per second. I'll see if I can maybe sketch that in here better. How about like this? Let's see what we can do here. In other words, that slope of that secant line right there is negative 40. Hopefully, actually seeing it as a graph like this makes it more clear why the slope had to be negative, why the average velocity here was negative. The mean value theorem guarantees that there is at least one time c between the starting point and the ending point where the velocity, the derivative of the position, the velocity, was equal to that mean velocity, that average velocity right there. And in fact, we found when that was. It was at time, was it 5/4? Yes. That time was actually at time 5/4, which is 1.25. And at that time right here, 1.25, comma, whatever this is, I didn't plug it in, its instantaneous velocity, its derivative of position, is exactly equal to the derivative to the slope of the secant line, the average velocity. At that time, it's going exactly the average speed. Before that, it was going slower. I mean, I could make my slopes of my tangent lines here, and they were slower. After that, it was going faster. But there is exactly one time it was going the same speed. That's actually a really important result in all kinds of applications. And it is true that in like later math classes and even when I was doing meteorology classes, every now and then you'd come across something and it'd say, you know, then by the mean value theorem, blah, blah, blah. But basically it's saying, you know, over this period of time, from time 0 to time 2.5, there was an average speed. Sometimes you were going slower, sometimes you were going faster, but you had to at least one time be going the average speed. If you're driving your car and let's say you're driving all the way you're driving up to Chicago for some reason, okay? The car is going a wide variety of different speeds over the period of time. Sometimes you're going fast, and sometimes you're going slow. So let's say this is time, and this is like how many miles you've gone. Alright? Sometimes you go fast, but then for a while you stop for a break and you don't go anywhere, and then maybe you're stuck in traffic and you go slow, and then you go fast again, and then you go slow. Here's your starting time, A. Here was your ending time, B. We could connect those two dots. You got all the way there at some average speed. I didn't connect the dots very well. But we could actually find the average speed. So like you drove 300 miles in 6 hours, you averaged 50 miles an hour. Sometimes you were going faster than that. See how your slope of your tangent line is faster than that? But sometimes you're going slower than that. But there had to be at least one, in this case 2 times. No, wait, that's not right. There had to be at least one, and possibly more, time when your speed was exactly the average speed. Where the slope of the tangent line is exactly the same as the slope of, it's parallel to, the slope of the secant line there. You can't average 50 miles an hour on a 300-mile drive without at least once along the way going 50 miles an hour. Sometimes you were slower, sometimes you were faster, but someplace along the way at least one place along the way had to be doing exactly 50 miles an hour. This is where it gets this name, mean value theorem. And again, is this the most important thing that we're going to learn in this semester? Absolutely not. But I know, for example, in Ivy Tech standardized test for this material, there are questions about mean value theorem, so we definitely need to make sure that we can do it. But are we going to get bogged down in like proving all these things later in the semester or when you take Calculus 2 or whatever, that you're going to be digging back into the mean value theorem? We're just not going to get all bogged down in that. Now, this section of your textbook does then proceed to spend some ink on corollaries of the mean value theorem. In other words, things that you can show that are equivalent to the mean value theorem. That's not even kind of interesting if we had lots of time, okay? If there weren't all kinds of other things going on in the world right now. So we're not going to get bogged down on that whole section about corollaries of the mean value theorem. That's just not the most important thing at the moment. All right. On Google Classroom, I've got a homework set posted for you and an exit ticket. I don't have it written down as exactly what the problem numbers were, but it'll be up there on there. And it's due fairly far into the future, but I don't know the date off the top of my head, and I will make sure that that's all posted correctly up on Google Classroom. You're going through a really interesting time in the world history right now. You're going to be telling your kids and grandkids about these last couple of weeks, and you'll be warning them about it. But you're going to stay on track, and you're going to be making great progress so that everything moves forward. If you have any questions from calculus to anything else, obviously, please let me know.